So in this section, 5.4, we're going to take a look at the relationship between the work done on an object and its gravitational potential energy. And so we might say the work done by a moving body, or the work done moving a body. So the work done is done by a subject. The body is the object. So the work done moving a body in a gravitational field at constant velocity. At constant velocity, that means the acceleration equals 0, is equal to the gravitational potential energy gained by the body. So the work done becomes the gravitational potential energy. So I'd like to point out that we said the acceleration is 0, and if the acceleration is 0, that means the net force is 0. So that means the forces are balanced. And if the acceleration is 0, put the wrong formula here, acceleration is delta V over delta T. So if the acceleration is 0, the change in velocity is 0. So constant velocity. So now let's suppose we have a pangolin, and that pangolin is lifted by a constant force at a constant velocity from the ground to a height z. So here's our diagram. We have the ground, like so. We have this pangolin, one of the only two bipedal mammals on the planet, highly endangered. So we have this pangolin and is being raised from the ground to this height up here over a height z. And we could say that change in height would be delta z, or the change in height of the height. What we see here in moving this pangolin is I've drawn a free body diagram, FBD, free body diagram, that shows the forces, the force applied raising it up, and the force of gravity acting downward. They are equal and opposite. So let's see if we see what's going on here. The net force is 0, so that means the forces acting on the body are equal and opposite. They must cancel. Because the acceleration is 0, constant velocity, acceleration is 0, no change in velocity, acceleration is 0, and if the acceleration is 0, the net force must be 0. That means when I sum the forces, add them up, they must add up to 0. So applied force positive, the weight, the force of gravity downward, must be equal and opposite. Okay, so the force that's doing the work here is the applied force. Well, we see our beginning force, the work, is the average force times the distance. Now the average force is the applied force, and the distance is the height z reached at the top. Now the applied force we know is also equal in magnitude to the force of gravity, or the weight. The weight is equal to the product of the mass and the acceleration caused by gravity. Now just a reminder that down here at the bottom we have the force of gravity, which is equal to the mass of the object times the gravitational field, or the acceleration caused by gravity. It is also equal to this second part of the equation, which is Newton's law of gravity. But in any case, the force of gravity is equal to the mass of the object times the acceleration caused by gravity. And so we said the work done is equal to the gravitational potential energy. So the work is the potential energy gravitational. And for the same reasons we saw with kinetic energy, that means that any change in potential energy is due to a change in height, or any change in height brings about, a change in z brings about a change in gravitational potential energy. And so we can see if we have some potential energy that is gained raising it all the way to z, well, that gain in total potential energy would be equal to the sums of all the smaller changes in gravitational potential energy, let's say from location A and B and C and D and E. The total potential energy is going to be equal to the sums of the individual potential energies. So a change in potential energy from, say, this location to this location is going to be due to that force applied over that height change, delta z. And so we don't need to have a starting height of 0, just a change in height, in the very same sense that we had a change in velocity bringing about the change in kinetic energy. It doesn't matter what the initial gravitational kinetic energy is. It's the change that is the result of the work. In the same token, it doesn't matter what the gravitational potential energy is when the pangolin started to determine the change in gravitational potential energy as it reaches a height z. Because in truth, the gravitational potential energy at the ground is not zero. Why, of course, that pangolin is on the ground, which is on the surface of the Earth. And so we have neglected the entire change in height, or delta z, from the center of the Earth to the surface of the Earth. So, just as that pangolin on the Earth has kinetic energy when it's sitting at rest because the Earth is rotating on its axis, it has gravitational potential energy because it is displaced from the center of the Earth. And that is our introduction to gravitational potential energy.